this simple workflow would be just an overview of some use case scenarios, either the real one or hypothesized ones. And then we will move in the second part of this afternoon slot before the break to also do a short demo of the QGIS tools that we can use to do terrain classification, terrain analysis, and in order to derive useful information that can help us defining a possible suitable landing site. So if you might know that there have been quite a lot of discussions about where to land the humans on the moon in the next missions. There were some proposed landing sites. In the end, we ended up around the South Pole, but one of the proposed landing site was Schrödinger crater, which is close to the South Pole, actually, not quite at the South Pole, but nonetheless very, very much interesting. And I would like to show you some layers of data that we can use in this place to try to do, let's say, an exercise on how we can characterize a landing site, both with data and with geologic mapping. So if you recall what Caroline said this morning on the first talk of the day about impact cratering, impact craters can be defined according to their size, and their size goes together with the inner morphology. The wider the craters are, the most variable are the shapes inside. Very large craters appear like peak ring basins. So if you remember, small basins, small craters have a ball shape. As they become larger and larger, they start to show a prominent central peak. As they are becoming even more larger, they show a peak ring, which is the case of Schrödinger crater. And you see that inside this crater, we have quite a lot of features. We have a well-pronounced crater rim, of course, and the peak ring inside is well defined, but not everywhere. But it divides basically an outer inner part of the crater floor, which looks very, very hummocky, rough terrain, full of small impact craters. And whereas the inside is much more smooth, you see that the texture here is very, very much finer. You don't see as many impact craters as in the outside part of the peak ring. And you see also other features like this sort of fractures, and also other features like this, for example, darkish halo around this depression, which is developed onto this fracture inside the crater. So we have talked yesterday about raster data, which are basically images. They are made of pixels, and each pixel may represent either a grayscale value, so shadow or light in case of a normal image, or they can bear other information, for example, the altitude information, so the topography. So I will show you now the DEM, or digital elevation model, which presents the altitude values overlaid on top of the images of Schrödinger crater. And this helps you identifying which is the higher part of the crater and which is the lower part. And also starts help also to define what could be the flat areas or the, let's say, more rough terrains. This is very, very much a first approximation, but is very, very much, let's say, I'd say mandatory to have a topography together with the highest possible resolution images to characterize a landing site. But at first, we want to focus on the big picture. We cannot just select a landing site by pinpointing our finger into a spot that we think is interesting, like, for example, here. It doesn't work like that, because we need to have the big picture. We have to know exactly how the surroundings look like, because we have to imagine that the spacecraft has to go down and pass over various morphologies and features before touching the ground. So we want to be sure that not only we are safe to land in a specific spot, but that then from that spot, we have to be able to move around safely and possibly effectively, both in terms of the say safety constraints for the mission, let's say to preserve our robotic mission or our humans, but also that the landing site we are going to is scientifically sounding. So the DTM is not always an information about topography, so what is high and what is low, but you can also process the DTM and calculate things onto this type of data to derive other types of information. For example, if we take the DTM, we can calculate the slope. This is a slope map of Schrödinger crater. And we can classify the slope according to degrees threshold. We can calculate and assign colors to the slope, which is 0 degrees, so essentially flat. Slope until 15 degrees, so lighter green. The slope until 30 degrees, we can decide to mark it in yellow, and above that in orange and in red, all the slopes that exceed 30 degrees, so 45 degrees and 60 degrees. This will help us tremendously in defining which sites are safe to navigate, so meaning that they are flat enough not to land and then topple down with our spacecraft, or that simply are too steep for our wheels to grip onto the lunar regolith, for example, and have enough grip to go up. This is just an example, but if you remember what Trent here said yesterday about the landing of the Perseverance rover, a similar job was done. The DTM, a high-resolution DTM, was created, a slope map was extracted, and then engineers that build up the missions provide you engineering constraints that help you to, let's say, constrain or remove specific areas that are too dangerous or too unsafe. You will see another beautiful talk tomorrow by Maurizio Paiola about this, on how to select a landing site on Mars. But at first approximation, this is a good idea. So having a topography and calculating the slope map. The slope map can be subdivided into slope thresholds according to our need. And later on this afternoon, I will show you how to do that in practice in QGIS. Of course, the topography, so the third dimensional information will help us to derive also other things. For example, the profile curvature. I have color-coded this map, which is the second derivative of the DTM, in mathematical terms, by highlighting in red the concave parts, in white the flat parts, and in blue the convex parts, meaning that everything that is blue is convex. The culmination of every object onto our surface, like that, is coded in blue. The concavities, so let's say the opposite, are coded in red. We have an immediate perception of what could be the dangers, so the depressions, the places that present holes or differences between the average topography and the lower part, or simply that are too concave or too convex to pass through. Maybe we want to go around them, okay? So this is a second order of approximation. There are many more, but this is another one that we can pay attention to. And you see that here you start to see other things. For example, before, if we go back, we see that, of course, the Pickering area is very steep. We have steep slopes, I think around 45 degrees or even more here. Here is around 30 degrees, which is a lot. You have to imagine that normally Mars rovers can climb up until 15 degrees of slope maximum, but the safe threshold should be around 10 degrees of slope. So these are completely outside our range of tolerance. We also have another information, if you look at the profile curvature, for example, is that the terrain around here is indeed very rough. It's full of depressions and culminations, depressions and culminations. It's very, very much variegated, whereas it is flatter on the interior part. You see, it's all gray. Only these craters, these holes, these the graben-like depressions are coded as convex or concave. It means that probably this area is smoother, maybe because it's younger. It's a younger infilling of the crater by some Mars basalt infilling, for any reason. But the important point I want to make here is that we can play with different levels of information: the slope, the topography, so the altitude, the roughness, the concavity and convexity, to build up a summary product. And you will see also tomorrow in a talk that I will give, a summary product that basically are telling you any information. You can go there, you cannot go there. These are the two things that in the end you want to arrive to. This is your objective. Today we also talked about compositions with Christian, Beatrice, and Francesca, and this is something you already seen this morning. This is just a reference for you, because all the previous things that I've shown you are basically providing you a safety threshold. It's the safety constraint. Whereas let's say the optical images and multispectral images are providing you the scientific constraints, meaning what are the important places where I want to go, and do the important places for science that I want to go match with the safe places where I can go or where I cannot go. So, for example, knowing the composition of a specific site inside this crater, and knowing that we can most probably land in the interior part, will help us narrow down also our scientific objectives. Because if we really strongly want to go somewhere here, but the engineers say no, the engineering constraints are not satisfied, we can forget about it. So it's better to play with the two in a very, very synergic way. And normally it's better to start with the engineering constraints, because the engineering constraints are basically telling you that you can go or cannot go there. If we narrow down the areas where we can go, we can then use, for example, composition information. This is a summary product that's basically telling you very, very few information, but that might be quite relevant. And we can land possibly in the inner part of the Pickering region of Schrödinger crater. We know from this color composition that, for example, red plus blue does purple, blue plus green does cyan, and green plus red is yellow. It means that if we have yellow, we have a combination of low titanium, high volcanic gas abundance, and low iron content. If we are in a cyan area, we have high iron content and high titanium content. In blue areas, we have high titanium content. This is basically how to read this map. And at first glance, we see that this area here has this sort of halo, which is yellow. It means that is low titanium, but high quantity of volcanic glass, possibly, and high iron content. If we go back, we see that this indeed is probably not a crater or not an impact crater. You see how drop shaped it is, how elongated it is, and it is placed on the major axis along this graben inside the basin. This is probably a volcanic vent with some sort of sputtered material, some ejected material. And possibly the volcanic gas is let's say, is the product of an explosive volcanic event on the surface of the moon. So this could be a very interesting point to go and check. So after we have checked our safety constraints and scientific sounding constraints, we know that we can land around here and we can try and see if we can reach this area. But of course, this is let's say a very first approximation. We need other types of data, maybe punctual analysis on high resolution spectral images. I'm not showing it there, but after having this broad overview, you have to go with higher detail instruments, for example, MCube on the moon or PRISM on Mars. You've seen it today. But you also have to build your own geologic map, because you need to know the relations. This is our possible landing spot, the relations between the different objects. And this is what Kramer et al. Did in 2013. This is the geologic map of Schrödinger crater. And you see that they made a stratigraphy starting from the bottom, so the older units, going towards the top, so the younger units. So you have Pickering material, which is the oldest one, and then the wall material, and then going up, smooth inner Pickering floor material, which is this one, which is where we possibly want to land, and then impact melt ponds, so small areas around the great impact melt, and then inner basin Mare unit. So probably this infilling spectrally is distinct, and indeed, it's quite clear that this part here has a distinct composition rather than this yellowish material here. And you see that they mark it as red, so inner basin mare unit. And then, as I told you, because I knew you already from this map, there's possibly a pyroclastic deposit unit around this depression, which is probably a volcanic vent. So you see how high the variability is in terms of geologic units inside this crater. We already know that we can go here inside this area, which is possibly the safer because it has less impact craters, the slope is okay, we don't have too many culmination, too many depressions, is quite variable. We have secondary crater fields as well. We can answer a lot of questions if we can go there. So we can make also a cross-section. Of course, if we build a geologic map, it's a good practice to do also a cross-section. For example, here from northeast to southwest, where you have basically exposed in section everything that you look from the top on the map. So the Pickering Basin, Mare basalt unit, which is the reddish one here, and then the pyroclastic vent here, Pickering, and so on and so forth. So let's say we land here because it looks safe. By the way, this is a very, very rough first demonstration on how you can approach such type of problem. Of course, you have to be much, much less qualitative than I am. You have to do the work that Trent did for the Perseverance landing. So the data should be very, very well registered. DTM should be very, very clean of noise and artifacts. You have to have very, very precise location of spectral signatures all around the location. But this is a very qualitative example of a possible workflow that you can follow. So let's place our landing spot here. Let's zoom in. If we draw a traverse of, for example, 200 kilometers, this is very long, but it's based on the old constraint from the Heracles mission foreseen by ESA in the past years. So a robotic mission driven by astronauts from an orbiting space station around the moon. We can land here, and if we cross the terrain in this direction, we can avoid big impact craters. We can touch this unit here, so we can have a look at pyroclastic deposits along this structure here. We can then cross secondary craters field. We can then enter this, which is, I think, inter-Pickering floor material, and then we can arrive until the Pickering here. And you see that the Pickering material is the oldest one. If we cross these types of terrains, we can answer to several questions. We can refine the absolute lunar surface chronology because we can collect samples and then we can bring samples back, analyze them, analyze the isotopes, and we can check what they are. What's their absolute age in terms of isotopic composition. We can check the nature of primary crust as well. We can have a look at the Pickering Basin, which is very old and coming from below. We can have a look at impact craters, and we can also sample the regolith, which is very important.
And on top of it, you may also have some material from the recent EP unit, which are not far away, that could have been redeposited via impact or as distal ejecta.
Exactly. If we draw another traverse of the same length from the same spot, we can encounter other terrains. For example, this red terrain, the inner basin mare unit, we didn't see it before, but we can cross it. Then we can touch again the secondary impact crater fields. Then we can enter the pyroclastic deposit. So we can have a sample, not only of the regolith, but also of the pyroclastic material, the volcanic glass that we suspect there's around this vent. And we can approach the vent and arrive until the very top of the vent. And we can answer other questions. Again, we can refine the absolute lunar chronology because, of course, we can collect samples. We can have lots of information about lunar volcanism. You have a Mare basalt unit here. And then you also have indications of pyroclastic volcanic events, which are not so, say, widespread or common on the moon. We can again have information about regolith. And also, since we are crossing a possible, let's say, pyroclastic event, if we sample it correctly, we can also try and see if we see some trapped lunar volatiles inside. So you see, you can answer very, very different questions if we cross the right type of terrains. And how you define the right types of terrains? Spectral images, optical images, and in the end, geologic mapping. And then you use the topography to assess whether you can go to these places or not. So this is a very, very first example. Now, we look to a real case, or let's say a future real case. This is hopefully. So this is the moon, this is the south pole of the moon. And you start seeing this is Shackleton crater. Permanent shadow crater, so meaning that the interior is completely in shadow all the time, whereas the rim and the ridge is in sunlight. There are permanent shadow areas, or also areas that are always in light, depending on the position of the sun. And of course, sorry, the animation started again. These possible landing sites were selected. You've seen it yesterday from Trent. They are 13, and this could be the landing site of our first coming back of humans to the moon, or with Artemis 3. This was taken by the NASA website, and you see that they are trying to land around the South Pole, and especially around these permanently shadowed craters, which could be, let's say, cold traps, so trapping ice and volatiles at their interior. And I'm showing this not only because it's very interesting, but because there has been some literature study, a very, very interesting study by Bernard et al., which studied these two sites in terms of safety, trafficability, and sounding of their scientific relevance. This is a topography again, so you see how variegated it is. You see that the rim of Shackleton crater, which is almost perfectly circular, is connected by this crater, by this sort of ridge. This is the Gerlachie crater, I think, yes, and this is the connecting ridge between the Gerlachie and Shackleton crater. And then you also have other sites selected for other types of reasons. We will go and see this area in particular. So this is the geomorphic map that Bernard et al. Did last year. It's published, and it's in the references in our GitHub page, which Angelo, we can maybe link it in the chat later on, so you can go and check the paper, which is very beautiful. And basically, what they did is a geomorphologic map. So in this case, they subdivided the units according to their morphology, not to their composition. Okay. You see that they identified different units: crater highland surface, intensely slumped surface, moderately slumped surface, elephant high terrain, crater floor. This is because they want to try and see if we can navigate and go around the specific sites to peek inside the Shackleton crater, and then also try to collect samples all around this area. And if we zoom in within this particular portion, you can see two things, one close to the other. One is the geomorphologic map again, and one is the slope map. Its color code is slightly differently than mine, and actually they put a maximum threshold of slope until 25 degrees. So meaning that everything above 25 degrees is coded in red. If it's 60 degrees, is red. If it's 90, is red. If it's 70, is red. So they have defined their safe, extended, a risky threshold of slope within this range of slopes, so 0 and 25 degrees. And you see that they started to trace a path along this ridge, which is connecting Shackleton, which is here, to the Gerlachie, which is here. And their wording here says safe, extended, and increased risk. So in line of principle, when you land on the surface of a planet, you want to land safely and you want to accomplish the nominal mission. So the minimum requirements for the mission to be considered successful. And so this is the safe part. So you'll go there and you are absolutely, let's say, not 100% because you're never 100% sure, but you are fairly confident that you can accomplish some scientific objectives in a safe way. If these are accomplished, you can extend your mission. You can maybe increase a bit the risk that you can take for mission failure. And then you can extend the mission for a certain amount of time, depending on how durable is the spacecraft or the rover or the suits, the autonomy of the systems, batteries, solar power, whatever. But normally there's an extended part of mission. This is also applying to satellite missions. Some satellite missions, for example, Mars Express has an extended mission since how many years, Angelo, now? 15 years, even more.
Well, max is almost 20.
So you can extend your mission if your systems are strong enough for indefinite time, if the resources are there, like let's say manpower and money to perform maintenance to the systems. And then the increased risk. So if you arrive here, the extended mission is accomplished, you can increase again your risk. You can try to cross higher slopes, a bit rougher terrain, try to go down and up, and maybe you can lose the mission, maybe not. The increased risk may have a different rationale. For example, I see something which is really, really groundbreaking. We can change our perspective on how we perceive the formation of the moon, whatever. There must be a good reason to increase the risk. But normally this is done just after we have accomplished our safe objectives. And here you see that, for example, there are some squares. Okay, these are possible sampling spots identified, and they are drawn a traverse crossing through them. Okay, if you see here, the safe spots are within the blue threshold, so around flat areas, flat or very, very moderate sloping. And then you cross here, and then you arrive to this slope, and then the slope increases. We are probably around 10, 12 degrees, so a bit higher. And then the slope increases again, and again and again. And then we are traversing in between impact craters, and then reaching up to the rim of Shackleton. The risk here is very high, and it's even higher where we start going down the rim of Shackleton on its outside to check this melt pool. So you see, slope is a good indicator of what you can or cannot do. You can draw a profile around your traverse path once you have drawn it. And here, this is what they did. They put together these two types of information: the geomorphic map, the scientific sites, and the slope. And you can plot it all together. For example, this is the landing site here, which is here. Key location. Other key location for sampling are the orange one and the green ones. This path is traversing different geomorphologic units, so the topographic profile is color-coded according to geomorphologic units that are traversed. Okay, so you are traversing the pink one, and then the green one, and then again the pink one. Then you arrive till here, which is the Shackleton rim, which is in yellow, which is this one, and then you go down this slope. And then you can plot together the slope, which is this one. So this is the altitude on the left-hand side. This is the distance of the path. And here on the other side, on the right-hand side, you can plot the slope. So you immediately know along your path on which unit you are, in the corresponding, which interesting site, and which is the slope that you are facing. And you see that everything that they did along this path is below the 15 degrees threshold. And you reach up the 15-degree threshold, starting from, let's say, the increased risk part here. Here you touch the first time on the Shackleton rim here, the 15 degrees threshold. This is probably the maximum threshold that they decided was acceptable for carrying on with the mission. So the traverse was designed to meet this requirement. The extended traverse slope was slightly lower, probably around between, let's say, 12 and 14. And the safe part, the slope, was less than 10. Okay, so this is what you can do and what we can play with to start to make a landing site study and a traverse study for this type of missions. You can do this exercise on Mars, and we will see tomorrow again a bit of an analysis of what Perseverance team did in the past months to drive the rover around certain objects or specific features on the surface of the planet. But this is an exercise that you can do basically anywhere on the surface of a planet if you have good imagery, if you have a good topography, and if you have a good geological, geomorphologic map. And so you can answer different questions, of course. In the safe traverse, you can see some ejector rays. You can have a look at local permanently shadowed areas. If we go back here, you can peek inside some craters, very, very small ones, which are permanently in shadow as well. You can see possible boulders from Shackleton Rim, so ejected from the interior on the outside, and maybe a larger rim of the South Polar Arctic Basin. If you extend the traverse, you start crossing the rim of Shackleton crater. You can see larger ejecta blocks. You can see inside the crater floor with instrumentation for detection of volatiles, water ice, or whatever. And then if you continue to risk your traverse, you can arrive to sample a crater rim and then going down and see other fresh craters. So you see how you can plan these activities. And now I pass the stage to Angelo, which talks a bit about the ground truth and exploration and mobility.
Thanks, Riccardo. I was answering to a question which actually makes a bit of the link with that. Basically, of course, I mean, what Riccardo was showing is an example, or actually two examples, which are very well documented of possible traverses. And the thing is that whenever we try and do this exercise, we are obviously limited by the engineering constraint, by the amount of time we have. And of course, we want to maximize the science. And in order to do so, of course, that's an exercise which can be tricky. On Earth, it's easier to go back with the car, on foot, with the donkey. But on planetary bodies, you cannot necessarily go back so easily, definitely at a longer time scale. So if you go to the next one, please. Rick. We have, I mean, not only for the normal, so to say, geological exploration, but also for the analog one, there are different conditions. And one of them, beyond the one that I already mentioned, is the fact that we are data limited. Some questions before were asked about, oh, is it 75 meters enough to make an accurate analysis? Well, yes, it's enough if you make the analysis until 75 meter resolution. Obviously, if you need the metric resolution for landing precisely your rover, like Trent showed yesterday, obviously that's different. So you are limited by your data, and that's something that we will also see in the next exercise in the next days, and also in the demo today, that we can say what we can say based on the resolution we have. On top of it, sometimes you have indirect information. For example, spectral data, you heard it this morning, you also heard the case from Riccardo today. Spectral data can be very valuable to tell you information about the composition, but it's still indirect, which means that you will have, of course, to deal with it in situ when you get there. And in general, yes, there is uncertainty that can be mitigated. For example, in the case of the lunar landing site, the human ones of the 60s, that was mitigated by a lot of precursor missions, even at the very same size. I think it was Apollo 12 that was landing close to a surveyor. So basically, this is something that you try and do with orbital data, or when you are very lucky with precursor slender data, but still there is much higher uncertainty than the Earth case. But you can still train, and all these exercises that Riccardo was showing from literature can be done, and actually are done on the analog setting. Yesterday, Trent was mentioning something about that, about astronaut operations, but that's something that you can do regardless of astronauts, also with payload, and testing the capabilities and how to perform ground truth in a traverse can be done. Obviously, with the limits that here you have a much better set of conditions than what you find on planetary surfaces. If you go to the next one. And that's more or less an example, a little view of the scale of the range of scales that you're facing. On the right, of course, on the bottom right, you see just a partial view of MSL. Now is much more. Same for Curiosity, but we are talking about tens of kilometers. And the same was actually for Apollo 17, the last Apollo landed mission. But if you look at the Apollo 11, which didn't have any rover and only had people on foot, you see that the scale, of course, is several hundred meters, probably more of total human traverses, but it's at a distance from the lander of just a few tens of meters. And this basically makes a big difference in accessing all the types of units that Riccardo was showing in the case of Schrödinger, and being able, of course, to fulfill more science objectives. But obviously, Apollo 11 was the first mission, so they had very tight and limited, so to say, success criteria, which actually they were met and even surpassed. If we move to the next one. That's the same traverse that you saw before, just with the backdrop of the L rock and with the different stations that were there during the exploration. So you see that there were kilometers away, the different stations, and in the scale of few days, basically, such a very large exploration could be done. So you can imagine that with future exploration and capable rovers, and both robotic and human, and you will hear about that on Friday by Matteo, and human crew, obviously the potential for doing sampling of a very diverse range of substrate and terrains and samples is there. And if you move briefly to the next one, that's essentially a simple reconstruction of, so to say, the story of the geologic context that has been then from such a path recovered, obviously post-mission, but partly also, pre-mission, because of course there was some context was already studied via orbital data. But basically this tells that every traverse then it's important if put into context. And all the samples, and you will hear something later by Fred, all the samples that are going to be taken by March 2020, of course, they're much more valuable because they are contextualized. And it's not just like a grab and go samples that you get there, you put it in a sample container and you leave, which is typically what you do in other cases, like exploring comets or other minor bodies. If we move on. So basically what you can do at the local scale, both for assessing your hazards and for getting information on the targets that you may face. Of course, it's analysis, which is the very same that Riccardo was showing, but that doesn't have necessarily be done at the scale of the orbital data, but also can be done at the scale of low altitude aerial data in the case of analogs of drones, or using panoramic data from rovers. So at the end of the day, the ingredients of the soup, so to say, are the same. It's just that the size of your vegetables in the soup are just smaller, but it's the same approach in terms of morphological analysis, stratigraphic relationship, topography, slope, ruggedness aspect, and all these kind of topographically derived parameters that can be extracted. And one thing that is very important for safety is, of course, the size frequency distribution of boulders or possible threats on the surface. And such boulders can be just measured by hand visually, can be done algorithmically, programmatically, or of course you can use, if you have available high resolution topography, or if you can derive it, for example, from shape, from shading and other photogrammetric techniques, you can actually extract them semi-automatically. And that's what also will be playing around and demoing later on in this hour and mostly the day after tomorrow on Mars. If you move on. Thanks, Riccardo. One of them, of course, is the topographic position index, which is an index that has been developed for geomorphology, so to say, applications, and like several topographic derived or morphometric parameters, can be very useful on the planetary case, because it's a way to describe the local context or the multi-scale context of the topography variation across a certain area along multiple directions that are so to say, around individual points. And of course, the individual points are each point of the image. And what you move around is the so-called kernel. And basically, when you do this operation, both with the TPI or with any other parameter, you are calculating some kind of proxy of your topographic derived parameter of interest, and you use it to interpret the local setting. For example, can be curvature, can be the degree of change of topography with the space, which is slope, and so on and so forth. Maybe at this point, Riccardo, it's good if I show a bit the repo, which doesn't have much here, or if you want, you can open it yourself, Riccardo. Maybe it's easier because you're already sharing.
Yes, this is just a...
yes, that's just an example of it. Go ahead, Riccardo, for free.
Yes, this is an example of a TPI. So again, what is high, let's say higher than the average topography, what is lower. So it's kind of similar to the profile curvature, but not exactly the same. At local scale, they look similarly. Tomorrow you will see, not tomorrow, but on Thursday on the Zero Crater, how you can construct a sort of morphologic feature map using this type of algorithm, meaning that you can extract the open slopes, the valley, the incised valleys, the mesas, the hills, the hilltops, the flat areas in almost automatic way, which is helping a lot in starting to narrow down our possibilities. What you wanted me to show now, Angelo? The JS project?
No, I just wanted to show the repo because there is the references of Kramer and Bernard have been added, and also there is some methodologic references, including the description of the DPI. So basically, that's at least the minimum.
If you can do it, I don't have it handy now. So
yeah, I do it. 1 second. Just give me. Can you see it?
Yes, we see your browser.
Yeah, exactly. Now, that's the repo. Well, there is some other material that you may find valuable, but in the Traficability, we put together some of the key references. That's a very minimum amount. There will be, of course, more can be added later on, but just as a guide of the things that you saw so far, for example, of how the topographic positioning index is calculated. Of course, we are not doing it by hand. We're using some routines that have been implemented in tools such as Sagagis, that is also embedded in QGIS. Of course, you could do it also coding it yourself from scratch, but that's not really what is needed. Sorry. And the two references that Riccardo was mentioning before with examples of traverses in different scientific targets on the moon are also included. On top of it, something that you will see in a moment is that there are some specific profile tool of QGIS plugins that can be helpful for performing analysis.